the connections between string theory, these Ambitwistor strings. I'll kind of use a /A for Ambitwistor strings, and the scattering equations at loop level. So Ricardo's given a very good exposition of these works that we've done in collaboration, and then they've done subsequently with Yvonne on what can you do with the Ambitwistor string and CHY at loop level. I'd like to kind of step back and question some of what I believe are open questions and actual open problems in these constructions, and especially I'd like to talk about modular invariance by the end of this talk, because I think it's actually an open question, at least in some context, and the result that we and they obtained on this nodal sphere expansion are correct because they have been checked. So I'm not challenging this in any way. I'm just opening the door to the possibility that they may be correct for a different reason than what we think, which would be what it is. But so that please don't hesitate interrupting me at any moment. Firstly, I'll be skimming the connection between strings and Ambitwistor strings. So that's actually some rather subtle points. I'd like to not talk about it for too long, but I'm happy to talk about it during the discussion. I just wanna get to the point that I want to use the Gross-Mende high energy limit to talk about the scattering equations, and I want to use this connection to explain why it's relevant to think about Gross-Mende. Because Gross-Mende we have under control, really, we know what it is, it's string theory, and that could give some way to understand or to locate the problems, if any, in the scattering equations at loop level. And then I'll come to the scattering equations at loops, really. One loop. Right, so I'll start straight away with a punchline for this first part, which I will materialize as a graph. So here there would be classical theories. This would be string theory, say Nambu-Goto string. Here, this would be null string or tensionless strings. So pay attention, I'm sending alpha prime to infinity. So when you quantize string theory, you traditionally obtain, well, string theory. But it turns out that this is an observation that's been remade by Siegel in 2015 in the context of this construction. But actually, this observation can be traced back to some papers from the 90s, that you have an ambiguity in the quantization of your classical action, and you can obtain a theory that Siegel called chiral or left-handed strings. With Eduardo, we studied these models, and we observed that they have some winding modes that actually break the chiralness. So we prefer to call them twisted, but it's the same. It's the same thing. Twisted strings. Of course, I'll explain to you what these objects are. And then here, if I follow the same type of quantization, I'd obtain what would be the Gross-Mende limit. So it's some kind of a theory of higher spins, but of course that doesn't quite exist in flat space, so I'm just putting quotes on that. And this would be the Ambitwistor string. So I'm very careful in this diagram to not connect string theory to the Ambitwistor string, as you see. It's not there's no direct way to go from string theory to the Ambitwistor string. The reason why I'm going to give you a bit of intuition of why this comes in here, but roughly the statement is that this is different quantum theories. So they have this one makes sense for sure. We know, right, as a quantum theory. Does the Ambitwistor string make sense as a quantum theory? It's an open question. Like Ricardo said, it's a really neat way to obtain loop integrands. So it says something about quantum field theory. But because it's just field theory, a priori you wouldn't expect it to be a good quantum theory. Because it's a theory of gravity, you wouldn't expect it to be a good quantum gravity theory unless you add some degrees of freedom in some way. Or they're somewhere hidden in there, which is actually maybe a possibility. So again, you may be worried that I'm sending alpha prime to infinity. The reason why this works is because, at least in the case of the type 2 object that you have here in this part of the diagram, the spectrum is truncated to exclusively states that are massless, to the supergravity states. So even here, on that side of the, even without taking any limit, I'm having a theory of string. It has left and right movers, but the constraints are such that there's nothing in the spectrum but supergravity. So it does nothing virtually to send alpha prime to infinity, and I'm not sending an infinite tower of massive highest spin modes to 0. It's just a cute coincidence. Nope. It's just really in the bosonic string and in the heterotic string, yes, but they're very moderate. They're very mild. But I'm going to comment on this now. So what is this quantization ambiguity? If we look at our, I'm just really looking at the Polyakov action. So our field has a mode expansion besides its 0 modes, alpha n over z n. And I'm not too careful about the normalizations. What you do usually when you quantize is you have to set a normal ordering, or you have to decide what's your vacuum in your theory. And usually what you do is you demand that the alpha n and alpha n tilde with positive n are annihilation operators. Sorry, yeah. That would be how you define your how you could go on and then do your quantization. There's another thing you could think of, which would be to set to take this condition for one half of the oscillators and put a minus here for another half of the oscillators. You're not changing the commutation relation. You're not doing anything. You're just declaring that this is now your normal ordering. So you'd put your annihilation operators on the right, and this guy would come on the right. It could, if you do that on both sides, by the way, it doesn't change anything. If you do it only on one side, it changes the things completely and really drastically. So you could think that if you consider that for a second, when you learned about string theory for the first time, you could think this is an absolute terrible idea. This is not going to work because this is going to create a whole lot of negative norm states. Because you're not changing the commutation relation, this minus sign here will screw up all your norms. Like if you look at your graviton, now the graviton would be alpha minus 1, alpha tilde 1. And when you take the norm of this guy, while this one would be correctly giving the good sign. When it goes on the other side, you'd have to commute alpha 1 and alpha minus 1. This one gives you a plus 1. This one is going to give you a minus 1. And the norm of the graviton becomes negative, and the whole of your spectrum is messed up. But it's not that bad. So you would dismiss that possibility unless you're really curious or you missed that fact. It's not that bad until you get to you realize it's good when you get to the constraints. So your Virasoro constraints. They're still L0 plus minus L0 bar. This is still the constraints you want to impose, except that now this guy is not ordered in the correct way. This is not the normal ordering. This is normal ordered. But if you want to normal order this guy, you need to commute these oscillators, right? Because I told you that this is now, this guy is. Did I mess up it? Did I mess it up? Okay. All right. So now I'm commuting these guys, and I'm looking at this guy plus the commutator. This is good. This is normal ordered. This gives me minus n, I suppose. Sorry, I'm going to have some sign troubles in this. Sorry. Right, okay. So now we have that this is still this zero mode piece. This guy here is minus the number operator. It's minus because I haven't changed my commutation relations. So when I act with this on a given number of alpha tilde n, it spits me the sum of the n's, but with a negative sign, because now I have the minus here. So this is minus the number operator. Let me call that with an upper script TW for twisted, so we don't confuse it with the normal number operator. And when you do this sum, you get minus 1 over 12. There's a minus here, making it a plus, and a d minus, 20, and a 24 for the 24 dimensions. So I'm cheating massively, but I mean, I'm going really fast, but there's a way to make sense of that computation. And if I have not messed up my signs, which I may have, now let's see what the two constraints become. L0 plus L0 bar, sorry, minus L0 bar. This one is usually the level matching condition. But now it's equal to, so the zero mode cancel. N plus N twisted minus 2. And that should be 0. So this is the truncation of the spectrum. The number operators, they need to be positive. And there's only 3 ways that this sum is satisfied. It's 1, 1, 0, 2, and 2, 0. And now the other constraint gives you the mass shell condition, so I'm not going to try and do this one. You get n minus n twisted bar minus alpha prime m squared over 2. That's 0. So these give masses, well, so okay. When it's 1, 1, it's mass 0, it's the graviton, okay? So I shouldn't write it like that. So the masses are 0, -2, and, okay, -4 over alpha prime, and +4 over alpha prime. So your whole spectrum for the bosonic theory is composed of 3 states. Yeah, we studied that with Eduardo. I'll come back on that in a second. This 2, it's going in the fact that positive plus positive equal 2 is either 1 and 1, 0 and 2, or 2, 0. Oh, the 2 is cancelled because, sorry, it's the 0-point energies that you need to also, sorry, I messed up the derivation. Okay. This guy should have been L0 minus, there is an L0 minus 1 and an L0 bar minus 1, and the L0 bar minus 1 becomes an L0 bar minus 1 plus 2, which changes the 0 point. Sorry, thanks for comments for the precision. Okay, so this is the spectrum of your bosonic theory, and the problem that I told you about before here is still there. This guy is a negative norm state. It's your graviton, so you're like, okay, well, too bad. But Warren and his collaborators observed that, so if this guy has negative norm, actually the norm is proportional to the norm of the vacuum. If you take the norm of the vacuum to be negative, the graviton has positive norm, but then these two have negative norm. So you're never really saved. And the content of this theory is some kind of a gravity coupled to massive spin 2. You don't really expect such theories to really be ghost-free or be sane anyway, so it's not too bad. Well, that's really gravity, and these are some massive spin 2 interactions. You can even compute the amplitudes in that theory. They make sense in the way that they have negative norm states propagating, but right. So and then so you would stop here if you thought, okay, maybe this was a good idea. Then you get there and you stop there. You're like, okay, too bad the miracle didn't go far enough. Actually, now if you do RNS, this guy just disappear. This is the only thing you get. Oh, sorry, I should mention the winding modes before. When you do windings, here you add a condition. You add an integer number here, NW. N is the number of Kaluza-Klein state, and W is the number of windings. This number can be arbitrarily negative, so it allows these two guys to be whatever they want. And your theory all of a sudden extends to a giant beast that's completely unexplored. We had a few. We studied a few properties of this with Eduardo, but it has loads of negative norm states and all. But it may still be worth investigating, because after all, if this theory had been dismissed because it had negative norm states, had not been dismissed, it would have led to the CHY formalism maybe 40 years ago. So who knows? Maybe that's an interesting sector of these theories. So this one is a tachyon, one is a positive mass, but both of them are ghosts. They go away when you go to the superstring, exactly. So now when you go to RNS, yep. When you go to RNS, or when you go to heterotic, it gets a little bit better. And when you go to the RNS, this guy, they just disappear, and your spectrum is supergravity. Excuse me? No, you get, in the bosonic string, I don't know. I don't know. Yeah, thanks. Okay, so in that sense, it makes that part of the arrow a bit less crazy. The spectrum has no dependence on alpha prime, so it's not going to do anything you send alpha prime to infinity. And by the way, even when you have dependence on alpha prime, it's quite small, right? You're sending alpha prime to infinity, you're just making these two states becoming massless. And then you obtain the bosonic ambitwistor string. I can't remember who gave a talk on the effective action of that theory last week, but it was work in collaboration with you, Nathan, I suppose, or? Oh no. When you send the mass of these guys to 0, they combine with the graviton into some complicated. But how do you know it doesn't have a subsector as an Einstein-Hilbert action? Just like the conformal gravity has a sort of subsector. Yeah, sure. So, I mean, for me, the picture should be this, really. It should work in some way, but right. I just want to show also now, I suppose, the connection to the scattering equations. Here. So, when you do this change of this thing here, you also change your propagators. So on the Worldsheet, you'd usually compute your correlation function of operators using the 2-point correlator that's just log of z minus z prime modulus square. Which is just the sum of this guy and complex conjugate. Yeah, so this whatever you have to do, they give you some traceless and usual spin type conditions on these states. There's no right. There shouldn't be any problem of normal ordering in the other LNs. So these constraints are just straightforward to apply. But we can discuss it afterwards if you want to see it technically. There's a nice review type paper by a group in Korea where all of this is treated really cleanly. So when you do this other quantization, you also change your 2 points propagator, and at this point you begin to be worried. You have a minus here, and that's log of z over z bar. And when you compute a 4-point amplitude, instead of obtaining a nice, say, Virasoro Shapiro type 4-point object, that's just the usual product of gamma functions, which we know and love, which in a sense we also celebrated the 50 years of in this very room a year ago, I guess. At least one half of it. Now you don't have this modulus square anymore, you have z over z bar type thing. I'm listening. Dualizing. Yeah. Correct. Yeah, you're kind of T-dualizing, but you're T-dualizing the whole of your non-compact space, including time, including the time directions, and then you don't really know what that means. So there's some super interesting open questions related to whether this model makes sense or not. And I'd love to discuss more to what extent what you're suggesting is some actually something to look at. Okay, I didn't know that paper. There's an old paper by Witten also, 88, where he kind of comments on that. But okay, but cool. We can, yeah. Thanks. So right, that integral doesn't converge. You can't just write it like that. You need to select a cycle. But upon doing so, you obtain that this type of objects are just a finite sum of poles. So that would be, okay, this is what I'm writing here is wrong, but it's the idea. I'm going to write morally. So, okay. This is 1 over S plus 1 over T plus 1 over U. This is the type of formulae that you get. No gamma functions. They all cancel when you do this thing. So again, that I should quote Siegel here because he really wrote that Siegel and his collaborators. That's quite remarkable, I find. And really, that here quotes again because that should be understood as a KLT type formula. So I shouldn't be elaborating too much on this because I don't want to spend time on one loop and modular invariance, but just to show you the scattering equations, roughly, I mean, there's a neat way to make sense of these equations, of these type of things mathematically, and Sebastian Misera has been digging up in the math literature a theory of twisted homology that we're now investigating together with him as well. Make sense of these objects as in a unified framework that connects the string amplitude, the Virasoro type amplitudes, to these twisted amplitudes. So that falls into a nice mathematical framework, and the way these objects come is also very clear. So you can really make sense of these integrals, except that you have to think of them as cycles, not just as beautiful surface integrals. But after all, Witten's been spending lots of energy also to explain, to insist on the fact that the correct formulation for RNS strings also is anyway a cycle, meaning that the integration cycle is also a middle dimensional cycle in a product of supermoduli space. So it's not too bad that the integral doesn't fall on the nose on something that makes sense. You kind of need anyway for the superstring to have something more complicated. If this is not d2z, but dz times some kind of dz prime, it's still a valid type of integral. Okay, but now let me comment on the scattering equations. The simplest way is to use the amplitudes. I could show you the constraints, but the amplitudes are simpler. No, the integral doesn't exist. Yeah, it's not exactly a direct product. There's this object known as the KLT kernel that mixes them, but roughly it factorizes, yeah. It's just like the open times open equal closed formula, except that for one of the open you have a different sign somewhere. Let me show you here. So at endpoints you have something like product of zi minus zj alpha prime ki dot kj. So zi tilde, I'm putting tilde to be a bit agnostic on what I define by these variables. Ki dot kj. Yeah, so this would be string theory. And when you send alpha prime to infinity, alpha prime ki kj to infinity, so it's fixed angle high energy limit. You get saddle point equations for these objects. So I should have written these with an exponential, really. How am I doing with time?
9 minutes.
Oh my god. Okay. So the saddle point equation tells you that you want the derivative of this object to vanish. So you take d on that, and you get nicely sum of the ki kj over zi minus zj 0. This is the scattering equation we've seen before. And roughly they're identical for the z and the z bars. And now of course you have all the other stuff usually in your integrand here. And when you do the localization, you get the usual nice exponential suppression in the physical regime, traditional string theory. But now if you do your minus thing here, well, you're not changing the saddle equations. The only thing you're changing is that the contribution from the phases, they cancel. So that's a non-trivial fact. But because this guy obey the same equations, roughly, when you localize, you take the difference of an object that's the same. It requires, this is a non-trivial statement because it requires showing that you have no cross product between different solutions. But this is something that falls in this theory here, or can be proven using this. And this is how you see that, contrary to string theory, when you take the high energy, sorry, it's not really high energy. When you take this localization limit in this twisted string, there's no leftover phase. So there's no exponential alpha prime s log s plus t log t. This is not there, because instead of having a 2 here, you have an s log s minus s log s plus t log t minus t log t. So they all cancel. You get no phase, and you get a rational function at the end, which is exactly the one that you obtain by doing the CHY or Ambitwistor computation. So this is where I wanted to get to at the end of the first part, to tell you that now we're going to look at Gross and Mende at one loop, because it's going to give us some information about Ambitwistors at one loop, because they share the same equations. Sorry? Yeah. Yeah, because these integrals are just really rational functions. So, if you know Gross and Mende by heart, you may be asking yourself, why am I talking about that? They don't use loop momentum. They just look at. So at one loop, the propagator is not log z, it's log of the function theta function, theta1, minus some factor times the imaginary part of z squared with the imaginary part of tau. And this is what there is here. So if I call this G, the string theory, you have G of Zi minus Zj. There's a cute thing to do, which was well known in the time of dual models, where people were looking at tube amplitudes. This term, you can trade it off for some loop momentum, and Docker and Fong insisted on that to show the property of what's called chiral splitting that holds at loop level. And when you trade this guy for loop momentum, this is it. Roughly you have an imz squared term, and you want to say that this is part of a L minus sum of ki im zi squared term in your exponential. L mu will be my d-dimensional loop momentum. So when I take the square of this guy, I recreate this dude here, except that I need to add maybe im tau and then im tau. So what I'm doing in this object that has log theta plus z squared, schematically, I'm adding a ddl so that this becomes product, I'll be removing all the alpha primes of tau im tau L squared plus sum of ki dot L im z plus sum of ki kj log theta 1 plus log theta 1 bar. When I complete the square of this extra Gaussian, of course I'm getting a power of im tau that's proportional to the dimension, but that's all taken care of because I should have written it here anyway. So there's no question here. When I complete the square, I spit out this guy with this power of im tau such that I really reproduce this propagator I had before. So virtually I have done nothing. Except that now I can take, so Gross and Mende would have taken the high energy limit here, and they have two types of saddle point equations. They have if this is my energy, it's some kind of it is an electrostatic problem. So it's my this is the energy of my distribution of charge on my torus. The saddle point are dz of energy 0 and d tau of the energy 0. Now I'm going to do something slightly questionable. I'm going to say I want to do the same here, but inside the loop momentum integral. The question is, the profound question is, do you have to do this or not? If you do it, so you fix the loop momentum, you forget about it. If you do it, you get the scattering equations of that Ricardo showed you before. You get a term that's L dot ki plus sum of theta 1 prime over theta 1 ki dot kj. And when you take the tau derivative, you get an extra scattering equation, L squared plus d tau theta 1 over theta 1, same thing. Of course, this works at G loops, right? You can write your loop momentum at G loops, and you can do the same type of thing. You get the loop scattering equations in the exact same way. So, just basic point so that this is clear. These scattering equations that you get in the high energy limit of string theory are those that you get from the Worldsheet model, from the Ambitwistor Worldsheet model. They are identical. Except that what really has happened here is not completely clear. Yeah. What? Sorry. You want a minus here? So like I've said, the framework is that the equations are not going to be changed. They will only cancel in the exponential. Although that's a bit speculative at loop level because it's hard to have an exact statement on what's happening here. I'm thinking how I should proceed given time. I'd like to say two things. I'd like to say that first off, in the context of gross. So what is modular? Okay, let me start with modular invariance. What is modular invariance? What are we doing here? I'm just going to look at tau, okay? Because this guy, roughly speaking, they fix the z's. This guy will fix tau. So in Gross and Mende, we started from something that was modular invariant before we introduced loop momentum. When we introduced loop momentum, it's broken, but it's broken for sort of obvious reasons. It's broken for the reason that it's broken in here. If you change tau to -1 over tau, that expression is not sent to itself, it's modified. But it's kind of trivial. But still, what you should do to absorb what's happening is you do a change of variable on the loop momentum, which is roughly as follow. L should be changed to, so if you change tau to -1 over tau, the new L that you should be looking at is tau times L plus some sum of ki, zi. Something like that. But now, what does it? My question is really, what does it mean to do it here, for the when you're localized on the scattering equations? Let me give you some piece of numerical evidence, because I've done lots of numerics on that. And with Eduardo, we published what made sense of it. I got plenty more of unpublished results, but they're not quite converging into some coherent story. So for the moment, I don't really know what to do. So first off, when you ask Mathematica to solve these equations, you solve and you solve and you solve, you find an infinite number of solutions. You shouldn't be surprised, because you'd think at first, well, I have an infinite number of replicas of the fundamental domain done here, so I should find an infinite number of solutions. There's one objective fact that arises quite quickly, is that you don't have the same number of solutions in each cell. So then you start to wonder, not sure what's happening. And even worse than that, sometimes, say, typical case at 4 point would be you have two solutions in the fundamental domain for some suitable issues in kinematics. But what happens is that sometimes, if you modify the loop momentum, so roughly this would be the IR and this would be the UV. So if you increase your loop momentum from slow to high, you'd have some sets of kinematics for which there isn't any solution in the fundamental domain anymore. So you have a set, the claim is that there exists a set of Ki and loop momenta such that this is empty. So then half of the room want to object to me. Fine. You just do a modular transformation to send them back up in there. But what does that? No, sorry, I'm sorry. I just really want to make this point. But what does that mean to do a modular transformation here? You're changing. You want to send this one up there and this one up there, but they're for different values of tau, which means that your L tilde here, your L, you're changing to, if this is tau 1 and tau 2, you change L to L1 and L2. What have you learned? You've just learned that there is a cosmetic change of variables which tell you that these equations would have been obtained if you had taken these values of the loop momenta, they would have been in there. But how does this tell you anything about your original question? It doesn't. Also, you have two different loop momenta where you wanted only one. So, to me, that's one piece of evidence that modular invariance doesn't quite work as you think it should. Another piece of evidence, some numerical work, when you track, so I'm showing you what happens when tracking one solution all the way from here to down there. It's for a 4-point integrand. That's just a scalar box integrand. So we're looking at something which is integral of d for whatever, dl, ddl over l plus l squared, l plus k1 squared. There's 4 propagators. It's this graph. I'm cranking up the loop momentum from low to big, and I'm looking at the integrand, the CHY integrand I obtain, by following exactly that solution. In the deep IR, this has a slope -4, and the slope -4 is for this -2, this is log scale. There's one -2, there's another -1 coming from, there's 3 propagators that will behave like L. L plus K1, this guy is just L squared plus 2L dot K1 plus 0 because we're on shell. So this guy gives you another power of L, this is -1, and there's the same for this one, which is L minus K4. Gives you another -1. So you expect a slope in the infrared, that's -4. Well, it doesn't matter if I went too quick here. In the UV, you expect -8 because you have -8 powers of the loop momentum. And this is what I find numerically, that the thing behaves like that. And the middle is a complete mess, and it doesn't match the scalar integral. So it's not the scalar integral. Maybe if you fit it, it behaves the same here, but then it does different, and then it's somewhere else. So it's not the full result for sure. But anyway, it's telling you that it may not be completely absurd to have to have been okay with crossing over from the fundamental domain to somewhere else, because qualitatively, this is something that makes sense. I couldn't go further because you have infinitely many solutions, you don't know really which one to take. I'm sorry, how much over time am I? Okay, I'm wrapping up. I'm just going to wrap up with, I had a nice toy example. I guess I'm going to wrap up with this nice toy example. Let's look at the saddle points. A typical saddle compact domain, so from -1 to 1. The saddle of that function is inside -1 and 1. And we're saying that f of x has some symmetry. It's doing whatever it wants, but it's like, this is my modular transformation. X goes to x plus 1. Now I want to break this transformation by adding a term. This is not symmetrical under x goes to x plus 2 anymore. But I'm removing this term with the loop momentum. So when I do this L integral, of course I get some factor that I need to cancel. But virtually, this minus x here is just not doing anything, because I could do the loop momentum. But now if I follow the same logic as I was following before, I run into a problem, which is that the saddle point in here, which used to be f prime of x equals 0, dx. I'm looking at large lambda, sorry. Now my saddle gets shifted to f prime of x minus 2x minus 2l. And this tells you already something. Say, I'm just going to plot the graph of f prime of x minus 2x. Say it goes like this. It has a sort of asymptotic minus 2 slope on top. This is 0 and this is 2. Sorry for changing. This is minus 1 and this is 1. You see that for two big loop momenta, you're integrating over the whole range here. But for two big loop momentum, you're trying to solve f prime minus 2x equals big. This is big. This is 2l. You're outside of the range. So it's telling you either you don't have solutions, or you're allowed to go this way, or you actually introduce a cutoff on the loop momentum if you want to do this localization.
Can you do the steepest descent on two variables?
Sure. No, okay. Of course. If you do steepest, no, but fine. If you do steepest descent on the two variables, you recover the same results, because anyway, this is a Gaussian integral, so it is localized. There's no question here. And the same holds true for Gross-Mende. If you do steepest descent for the loop momentum as well, you just recover usual Gross-Mende. So, a numerical piece of funny evidence for some, I tried a few, there may be some sort of general lemma, but I've tried a few Fs here, and one solution that seems to work is to truncate, is to tell that you truncate your loop momentum integral. You truncate it here, you localize in X, you do the truncated integral here, and then you seem to recover the same result. So I'm sorry for not presenting a theorem or something. This is just going in the opposite direction as what I was saying here. Here I was saying you are allowed to follow all the loop momenta from the IR to the UV. And here I'm saying, actually, maybe the correct answer is to have a truncated integral for the loop momentum. Roughly, this is where I want to end. There's a paradox. I have no idea how to really, what's going to happen, what's the best, or what, maybe both pictures are correct in some different senses. This picture would tend to go in the direction of saying, if you restrict your tau, if you really insist that tau is sitting up here, you can't integrate over all the loop momenta. But what then is the shape inside loop momentum space that you should select? Completely open question. Also, the conditions of what this boundary look like in loop momentum space seem completely hopeless to determine even numerically. Okay, so yeah, I'll stop here. Sorry. Yeah, I'm sorry. Sure. Thanks. Sorry for going.